An electric arc burning at 3,000 degrees Celsius, submerged in the freezing ocean, seems to defy every law of thermodynamics. Yet this is the very foundation of industrial underwater welding. This incredibly dangerous operation is critical for maintaining infrastructure like oil platforms and transnational pipelines, and the International Marine Contractors Association records confirm its absolute necessity.
It's an extreme dynamic, isn't it? When a welder strikes an electrode underwater, they're not simply joining two pieces of steel, they're initiating a controlled chemical reaction in an incredibly hostile environment that constantly works to strip heat from the weld pool. Naval engineering has broadly categorized this into two main approaches since the 1960s, driven by the offshore oil industry's growth.
And the first of these is hyperbaric dry welding, or dry welding, which sounds almost counterintuitive for an underwater operation. How does that work?
With dry welding, engineers install a watertight chamber, a habitat, around the section of pipeline or structure that needs repairing. They then completely expel the water by injecting artificial gas mixtures at a pressure balanced with the outside. The welder works inside this dry environment, which eliminates the rapid cooling or thermal shock that water would otherwise cause.
So a habitat offers a level of metallurgical control comparable to a surface laboratory, allowing for excellent quality joints. Technical reports from the offshore industry show this technique is crucial for high-pressure pipelines deep underwater, but the logistical and economic effort involved sounds enormous.
It certainly is. Constructing, lowering, and then sealing a custom-made habitat at, say, 300 meters depth demands support vessels with heavy lift cranes, complex saturation systems for the operators, and weeks of preparation. The alternative, which trades some environmental control for speed of intervention, is wet welding, or wet underwater welding.
Wet welding seems far more direct, removing any physical barrier between the operator and the ocean. It's used for emergency repairs, like damage to ship bulkheads, I understand.
That's right. The welder is directly immersed, using an electric arc process with a shielded electrode, technically known as SMAW, or shielded metal arc welding. The biggest hurdle with SMAW in water is maintaining a stable arc when the water tries to extinguish it instantly. The solution lies in the electrode coating's chemical makeup. Burning at extreme temperatures, this protective flux vaporizes the surrounding water, generating a microscopic gas bubble.
A gas bubble underwater? That's quite a feat. What's it composed of?
It's mostly hydrogen, carbon monoxide, and oxygen. This gaseous capsule temporarily isolates the arc and the molten metal, providing the milliseconds needed for the liquid steel droplet to transfer from the electrode to the joint. While this bubble solves the arc extinction problem, it unfortunately introduces one of the most serious metallurgical threats in underwater welding: hydrogen embrittlement.
Hydrogen embrittlement, the invisible enemy, as some call it. Material science manuals describe it with merciless precision. What exactly happens?
Under the arc's heat, the water molecules within that protective bubble undergo thermal dissociation, separating into oxygen and atomic hydrogen. Atomic hydrogen has a tiny ionic radius, allowing it to easily diffuse into the molten metal of the weld bead. The surrounding water cools the metal at a rate dozens of times faster than air, trapping this hydrogen within the steel's crystalline lattice before it can escape.
And this trapped hydrogen then causes internal stresses within the metal, leading to invisible microcracks.
Exactly. When hydrogen atoms recombine into molecular form within the metal's imperfections, they exert enormous pressure from the inside out. This forms cold microcracks. invisible to the naked eye, which compromise the joint's mechanical resistance. A weld that looks perfect can suddenly fail under load, leading to a latent structural disaster. Metallurgical engineers try to counteract this by developing electrodes with water-repellent coatings, often based on rutile or oxidizing compounds, to alter the gas bubble's composition and limit hydrogen absorption. But the risk remains inherent to the wet process.
So the danger isn't just internal to the steel, is it? That gas mixture, generated by the electric arc, disperses as bubbles. What are the wider implications of that?
The danger extends beyond the microstructure. Safety inspections have documented numerous accidents caused by these bubbles accumulating inside structural pockets, cavities, or submerged blind pipes. Trapped hydrogen and oxygen form a highly explosive mixture, and a single stray spark from the welding can trigger a devastating deflagration, capable of generating a lethal shockwave for a diver operating nearby. The physical management of the construction site absolutely requires a preventative analysis of all potential gas vent paths.
Beyond chemical and explosive risks, working with electricity in a conductive medium must require extremely robust safety protocols.
It does. The operator handles an electrode carrying hundreds of amperes, protected from electrocution solely by their rubber insulation and strict power management. Commercial diving has codified a vital control system centering on the tender, the surface operator assisting the diver. The welder's connection to the support vessel is via an umbilical cord, providing breathing gas, radio comms, hot water, and power cables. Crucially, the control of the current flow is never in the welder's hands underwater.
The tender holds all the power, literally. They operate what's called a knife switch, a massive bipolar safety lever that's strictly kept in the open circuit position.
Exactly. Operational protocols demand standardized, unambiguous radio communication. The diver positions the electrode and gives the vocal command, quote, "make it hot," end quote. Only then does the tender close the circuit, energizing the electrode holder. The moment the welder detaches the arc, they immediately order, quote, "switch it off," end quote, and the tender cuts the power. Any autonomous operation without surface support is effectively ignoring the fundamental physical rules of the hyperbaric environment.
So improvisation is simply not an option. The regulatory frameworks must be incredibly stringent.
They are. CEDIFOP, the European Vocational Training Centre, clearly distinguishes amateur activity from industrial profession. A basic commercial diver certificate isn't enough to access welding tools. Regional and international directives demand a background in deep diving. For instance, Presidential Decree No. 31 of 2018, implementing Sicilian Regional Law 07 of 2016, mandates registration in the Telematic Registry of Industrial Diving. This requires skills equivalent to Level 2 of the international IDSA standard.
So a student must master using a rigid helmet, surface supply configuration, and emergency maneuvers under stress before even beginning to approach the complexities of underwater metallurgy.
Precisely. IDSA Level 2 certifies the ability to operate with surface-supplied equipment, ensuring a candidate has the spatial awareness and experience to manage a tangled umbilical in the dark, often with strong marine currents. Training records show that teaching welding to someone without these operational foundations dramatically increases the probability of fatal accidents. CEDIFOP training merges metallurgical theory with industrial practice, requiring candidates to perform weld beads evaluated through testing identical to inspections by ship classification societies and specified by the UNE-N ISO 15618 standard.
And the actual working conditions themselves must be incredibly challenging, even for the most highly trained individual.
Beneath the surface, visibility is often reduced to mere centimeters due to stirred mud or turbid water. The operator relies on touch, the sound of the frying gas, and the glow of the molten pool through the opaque suspensions. Maintaining arc length, electrode inclination, and travel speed becomes an internalized biomechanical movement, performed in zero visibility and hindered by the water's viscous resistance. Muscle memory has to compensate for the complete absence of clear visual references.
This combination of sensory adversity and physical constraints confirms that an underwater welder functions as both a precision craftsman and a survival technician. There's no room for error. A valve malfunction, a misinterpretation of a metal defect, or a slipping communication with the tender has immediate consequences.
That's true. The submerged infrastructure upon which the global economy rests, from offshore wind farm turbines to continental gas pipelines, relies on the integrity of these joints, executed in a hostile and implacable environment. Underwater welding exemplifies that operating in the deep demands rigorous scientific protocols, where survival and industrial results are inextricably linked by the same discipline.
If this exploration of thermodynamics and offshore safety has offered new perspectives on underwater infrastructure, share the episode with someone interested in extreme engineering.